So back to the M&M problem. So we have bags of M&Ms that are 20% red. Okay, so I simulated using StatCrunch, like drawing from a bag that was 20% red. Okay, so I did this 1,000 times, and I made a dot plot of all of my sample proportions. Okay, so what I have here is the beginning of a sampling distribution. Again, I don't have I don't have a complete sampling distribution because I've only done 1,000 samples. These all are size 20. Okay, and if you notice, this mean comes out very close to 20%. And again, that's the population mean of my sample proportions. Okay, and my standard deviation, which would be called my standard error, is about 8%. Okay, so this is just an example of if you were to take a whole bunch of bags of those fun-sized M&Ms, calculate the percent of them that are red, and made a dot plot of all your sample proportions, you should get a graph that looks similar to this. I had one bag, or one time I had no reds at all out of the 20, but up here I had a time where I had a bag that actually had 10 reds out of the 20, or 50% were red. So these things don't happen very often, right? Okay, if you notice, I have mostly 20% reds in the bags with a little bit sometimes on each side of it. And as you get these extremes, they're not going to happen very often. So this is the example of a sampling distribution. Okay, so the mean of all the sample proportions would always equal the population proportion. And again, this is if you do simple random samples, okay, and if you could actually do all samples of the same size from the given population. Okay, the standard error will be smaller if you have larger sample sizes. That should make sense because if you sample more people, you're getting more accurate results because you're doing more of the population. Okay, and again, here's that same notation that I've talked about. The mean, so this will be the population mean of all the sample proportions. This will actually equal to the population proportion, which we call P, okay, and the standard deviation of the sample proportions, which we call the standard error, we can abbreviate like this. So it's the standard deviation of all the sample proportions, or otherwise known as the standard error. Okay, when you do this, population size actually doesn't even matter. Okay, so the size of the population has no effect on the distribution of all the sample proportions as long as the population size is at least 10 times larger than the sample size. And if you think about when they do samples of the entire U.S. and even adult population, or those to vote, their population size is huge, so it doesn't take much to have a population size 10 times larger than your sample size. Okay, so if you look here, I have 2 bowls of soup, a small bowl and large bowl. These represents a population. Okay, so do I need to take more spoonfuls out of the large bowl of soup to figure out what it tastes like? Probably not. You should just, as long as it's well stirred, you should be able to take 1 spoonful out of either bowl and you know what it tastes like. Okay, I can use the same size spoon. So that's the whole idea with it doesn't matter what the population size is. So if I want to find how like people in Ohio are going to vote in a certain election, I could take a sample of size 500 and I'd have just as accurate results as if I wanted to figure out how the whole United States was going to vote on certain issue, on a certain candidate or whatever, and I'm doing a sample of size 500. It doesn't matter. I get the same results doing the same size sample, even though the one population size is a lot larger. Okay, I refer to this as my soup example. So if you get a homework back from me and it says remember the soup, this is what I'm referring to. Okay, population size does not matter. It's only the sample size that matters. Okay, so here's the example I just gave. The fact that you can do a sample size 500 from Ohio and it's just as accurate as a sample of size 500 from the entire United States. Okay, so if you do a simple random sample, your bias should be 0. In other words, it should actually hit your target, or your sample proportion should be very close to your population proportion. Okay. Remember, it may not be exactly equal to it because you have what we call sampling variability that comes into play. Okay. The precision is going to be better for larger samples, so you're going to be even closer to the whole the larger your sample is. Okay, and precision and bias are independent of the population size. Again, as long as the population size is at least 10 times larger than the sample size. So if your sample size is 100 you just need a population size of 10. But normally we work more with population sizes of 1,000,000. Okay. I think I just said that wrong. If your population size is 100, right? Let's do 1,000. If your population size is 1,000, right? It needs to be at least 10 times larger than the sample size. So this is work as long as your sample size is 100 or less. Okay, I think I said it the wrong direction the first time. Okay, so here's the formulas that we're going to be using, because eventually we're going to try to estimate our population proportion based on our sample proportion, but we're going to end up coming up with an interval. If you think about a lot of the polls that you've seen, a lot of times they say they have a margin of error of like plus or minus 3%. Okay, so that's what we're going to try to do at the end of this chapter, is we want to build what we call confidence intervals. Okay, so this is what a little bit I've already talked about. My mean, my population mean of all the sample proportion is going to equal the population proportion. Okay, the standard deviation of all the sample proportions is actually going to be equal to this here, where P is your population proportion and N is your sample size. Okay, now if your sample size is increased by a factor, then the standard error will be decreased by the square root of the factor. Okay, so if your sample size is quadrupled, that's increasing your sample size by a factor of 4, then the standard error will be cut in half, right? It would decrease by the square root of that factors. Okay. Okay, so about 20 million Americans attend college each year. About 12 million, or 60%, borrow annually to help cover costs. If many random samples of 500 American college students were taken about college debt, what would be the mean and standard deviation of the sampling distribution? Remember, in real life we only take one sample, but in statistics class, again, we're going to talk about taking many samples so that we know if we take one sample, that one sample should be accurate. And again, all of this is based on taking a simple random sample. Okay, so the mean of my sampling distribution, remember your sampling distribution is that collection of all of your sample proportions. Okay, so I take a whole bunch of samples of size 500 and I look at the proportion in each of those samples of the students who have to borrow money to help cover cost. Okay, most of them should be around 60%. So what's the mean of all those sample proportions? It should be about 60%. Or okay, if I actually can do every single sample of 500 possible, it actually would equal 60%. Okay, the standard deviation, or the standard error, because now we're talking about a sampling distribution, that's the standard deviation of all my sample proportions. I'm going to use this formula, right? My population proportion is 60%, so you should try this on your calculator. Okay, make sure you get the right answer when you're doing this. Okay, when you put it into your calculator, make sure you hit divide by 500, you hit the equals before you hit the square root. Or if you have a graphing calculator, you can put this in exactly like it shows. Square root, it'll put a beginning parentheses in for you, and then you just need to type this in. You may have to hit a time sign between the 0.6 and before you do this parentheses, especially if you have just a cheap calculator. Graphing calculators you would not have to. Okay, if it's scientific calculator, I think most of those anymore you don't have to, but you may have to hit the time sign here before you can finish on. You should come up with 2.2%. Again, I converted this to a percent already, so you're going to have 0.022, or depending on how, I don't remember exactly what it comes out to start with, so I may have rounded this to, so you might have something slightly different, but it should round to 2.2%. And again, you're going to get a decimal out, which would be 0.02. Okay, so what's the trouble with using P? Well, we don't normally know P, because if we knew the population proportion, why do I need to do a sample? Right? Okay, so what we're going to do is, so the main application of the sampling distribution is address the bias and precision of a sample that's taken. Okay, the purpose of taking a sample is to estimate the population proportion, so normally P is going to be unknown, so I have no way of calculating my standard error, because I don't know P. Okay, so what we do is we use P hat instead as an estimate for P. So my standard error, the estimate for the standard error becomes P hat times 1 minus P hat divided by N. Remember, P hat is your sample proportion and N is your sample size. Okay, Now, in section 7.3, we're going to be using more of this information. We're going to be still using those same formulas. Okay, and we're going to talk about the central limit theorem.